So our next lecture is upon ratio rules. What are radius ratio rules of ceramic crystals? These are the following three, in which number one explains we will consider ions, not atoms, in ceramics crystal structure. Beside that, cation is the positive one and have smaller size as it give up electrons to metallic ions or anions, and anions are negatively charged. They are negatively charged, and they are greater in size. They accept the electron. These two components are then usually in these two components the characteristic structure of crystal structure of ceramics depends. So in what ways we can see here? Number one, the electrical charge magnitude on each component of ions and the relative sizes of cation and anions. Electrical charge should be balanced. For example, if we take the example of CAF, in which you people know that CA have valency 2 plus and F has valency minus 1, so these are not balancing each other. It should be another added another fluorine to get the balance valency. And the number two, relative size of cation and anion. It means the radius ratio of cation to anion should be less than 1, as cation are smaller in size than anion. Besides that, we will discuss some stable and unstable structure of ceramic crystals, in which the ions are in touch to the surrounding ones, are stable ones. These two are, and in the other one which is here and it's not touching the other four is unstable one. So this was the radius ratio rules of ceramic crystal structure. The next thing is nothing but the coordination number, cation to anion radius ratio, and coordination geometry. So for coordination number 2, coordination number means nearest neighbor. Nearest neighbor 2, if there are two nearest neighbor and the ratio is 0.155 or less than 155, the geometry would be linear. Like this, we have a cation in the center and the anions in the surrounding. For coordination number 3, the range of cation to anion radius ratio is 0.155 to 0.225. It would be triangular planar, in which 3 are in a plane and 1 is at the void. Or you can say that one cation is surrounded by 3 anions. For 4, this is the range, and the structure geometry would be tetrahedral. Tetrahedrally, there the 3 are in a plane and this above it's on another plane. So for coordination number 6, we have this range and octahedral structure and octahedral geometry. Octahedral mean there are 6 ions and 8 phases. For coordination number 8, this is the radius ratio geometry. Radius ratio cation to cation and radius ratio, and this would be a simple cube. So now I will discuss some exceptions. The exceptions are that it's not like that you will always get a coordination number 4 if the cation to anion radius ratio is between 0.414 to 0.732. For greater than 0.414, you might have the coordination number of 4 instead of 6, because there are some exceptions in ceramics in which the bonding is highly covalent. Then the size of ion is directly proportional to the coordination number. If coordination number is increasing, size would increase. The radius ratio depends on charge. If the charge is increasing, and then radius ratio is increase. To some extent, we can say that large or increased radius ratio, and for this is for especially for anion, in which they accepts the electrons, and the size of the um, uh, respective element would increase, radius ratio in turns would increase. And similarly for cations, or the elements whom electrons get lesser, you have decreased radius ratio. So radius ratio would depend on the charge. This was the coordination number dependence on cation and radius ratio, and coordination geometry also. And after that we have just looked at some exceptions, and dependence of radius ratio on charge, and size of ion also depends on coordination number. And before that we have just had a look on radius ratio rules. What were that? Thank you for watching this.